So for our activity number 5, we are going to design a 4-input hexadecimal decoder circuit with the following specifications. First is the use of RBO, RB1, RB2, and RB3 as inputs with pull-down resistors. Next, the use of port C as our output port that is connected to the common cathode 7-segment display. And lastly, we shall follow all the steps and procedure in creating the design and output video presentation. So this is the output in the common cathode 7-segment display that we're going to achieve for today. So let us start by examining first the source code that we're going to use to upload. As you can see, here is our activity number 5. And first we define assembler constants in which we equate the name of the register to its address. So status register is 03H, trace B is 86H, port B is 6H, trace C is 87H, port C is 7H. So we have here the general purpose register count 1 and count 2. So equated to 21 and 22H respectively. And then we equate the decimal value 5 to RP0 and the decimal value 6 to RP1. So in the second part, we use the OR directive to force the program to start at the reset vector. And then next, we set and initialize the ports. So set port B and port C as usable ports. So depending on the usage, we're going to set port B and port C. First, we clear the W register. Next is we clear the RP0 bit and then the RP1 bit of status register. So take note that when RP0 is equal to 0 and RP1 is equal to 0, it selects bank 0. So in bank 0, we can now access port B and port C. So the clearF command will clear the register of port B and port C. So this will also initialize the following ports by clearing output data latches. So if in the previous program uploaded to the microcontroller, these are used as input or output, it will be disregarded and it will be reset. So next, so once the status registers are now clear, so for particularly RP0 and RP1, we now set the status register bit 5 at 1. So with this, we are now selecting bank 1. So we move the literal 0x00 to the W register. Next, from the W register, we move the value to both trace C and trace B. Next, after setting the 5th bit of the status register, we are now going to set the bit 0 trace B as 1. So set means 1. And then the bit 1 as 1. So when both of that are set to set as 1, so it will be used as an input. So 1 is input, 0 is output. So we set the following bits, so the bit 0 and the bit 1 as input. Next is we clear the 5th bit of the status and then the bit 6 of the status register. So the value of that now is 0, 0. So this will initialize or it will trigger the bank 0. So it will now access bank 0. Previously we accessed bank 1. So bank 1 we access the trace C and trace B and the status. So when we access bank 0, we can now manipulate port B and port C. So here, in the flowcharting program, this is our decision part. So here, the following bits are being examined. So for the first part, bit 3 or the 4th digit or the most significant bit is examined. So if the bit 3 of port B is 0, this line will be skipped. Otherwise, it will go to FXXX. So after that, we examine the bit 2. So put simply that we go here at TXX, it means that the first digit or the most significant bit of the input is 1. So it will go here. On the other hand, if the first bit is 0 or the most significant bit is 0, it will go here. So this is the pathway of the program. So next, we are leading from bit 3, we are now going to bit 2. So we will examine now what is the value of bit 2 of the port B. So BTFSC port B is equal to 2. So if the bit 2 of the port B is 0, it will skip this line and then go to this one. So that means the value is 1, 1, and then XX. XX means not yet known or it is not being considered as of this moment. So from this line, we have the following label at the next part. So for this one, if the first bit or the most significant bit is 0, it will also have two pathways. It will either go to this one, wherein the second bit is 1, or it will also go to this one, where it is also 0 on the second most significant bit. So considering the next part, we have 4 scenarios for the following. So we have FTXX, FFXX, TFXX, and TTXX. So the following bit is considered. So the bit 1 or the second least significant bit is being considered. So for this one, we have 8 pathways. So from that 8 pathways, it will either go through to one of these. So here we have different values assigned. So we have all the values from 1 to 15 or 1 to hexadecimal F. So let us simulate the program. So for the value 0, 0, 0, so let us try and simulate the program. So it will examine the bit 3. So in 0, 0, 0, the bit 3 is 0. So here it will skip this line and then go to this line. So it is correct because it will go to the 0, 0, 0, 0, 0, which is also classified here 0xxx. So from this it will go to fxxx. So it will also examine or test if the value of bit 2 is 0. For 0, 0, 0, 0, the bit 2 is also 0, so it will skip this line and then go to this one. So let us find fffxx. So from this one, we have possible 2 scenarios. If the bit 1 is also 0, it will skip this line and then go to this one. So this is 0, 0, 0, x. And then let us find fffx. We have 2 possible scenarios. If examined that the bit 0 is 0, it will skip this line and then go to this one. So we can now say that this is our value. So from this one, it will go to this one. So it will move something from the W register to the port C for the hexadecimal display to be outputted on. So let us recall that in the first part of the activity, we have already converted the bits of segment A to G to hexadecimal so that it will be ready for use when programming. So we have 0 as 70, 1 as 30, 2 as 60, 3 as 79, 4 as 33, 5 as 5B, 6 as 5F, 7 as 70, 8 as 7F, 9 as 73, 10 as 77, 11 as 1F, 12 as 4E, 13 as 80, 14 as 4F, and 15 as 47. So we have additional one, which is the delay. It uses the decrement, the count 1 register, and then save it to the register itself. So it will skip this one if the value is 0. So we have 255 cycles for this one, and then another 255 cycles before it returns. So if it returns, it will exit the loop, the nested loop. So this is the end of our program. So let us look at the previous activity. So this is the previous activity that we have done. So let us wait for the program to load and some of the details for this program, because this also uses the same microcontroller unit, and then we're also going to be needing the power supply circuit. So first of all, we need to edit the details. So here, this is activity 5, then detail 24, 28, 2021. And then we are just going to be needing the up to bit 3 because only 4 inputs are needed. And then let us remove these resistors, and we are going to replace it with a common cathode display. So remove this one, remove. So place, we need to click here at the parts, and then common cathode 7-segment display. So 7-segment display. So this one, click OK, then place it here. Then we are going to be needing 220 ohms resistor. So min res 220. 20. So place it here. So let us copy again. Right click, block copy. So connect this. Connect. So for us to be sure, we should connect the endpoint to endpoint. Then we're going to place a terminal. So you can find the terminal here. So we need an input terminal. So from this one, upward. So copy, then paste. Select this one, block copy, and then do it for other pins as well. Okay. Right click so that it will exit. Select only this input, and then we're going to click it as well. Connect the one pin. Okay, so we're going to put labels on this one. So this is 0, 0. Then this is C7. So we should follow it. C1, C2, C3, C4, C5. Oh, I'm sorry, it's C6 because we have bit 0. Then we're going to put ground here because this is a common cathode 7-segment display. So select it here and then place it. So we are also going to connect. So aside from that, we're going to be needing the pull-down resistors. So since we are going to use port B as inputs, we don't need output terminals. Instead, we need input terminals. So input terminals can be found at the terminal. So let us rotate this one. Rotate 180 degrees. And then let us copy this. Copy to the port and then paste from it. So select this and then copy. We can use block copy so that it will be faster. So here, okay, I almost forgot. We only need 4 inputs because this is a 4 input decode. Decoder 4 input hexadecimal decoder. So you connect this one and then connect this one. So we move here 6 trees. And then we're going to name this RB0. So that will fix the case RB0, RB1, RB2, and then RB3. Okay, the last thing we're going to do is to create a two components and then click P. So main res, we're going to be needing 10K resistor. Okay, place that. And then push button. We already have one here. Okay, that's all. So let us place the push button. And then the resistor. So main res 10. So the resistor is pulled down to the ground. It's very important to have this kind of setup so that our input pins will always receive a signal 0. So let us insert another input pin. Place an input pin for power. For this case, I'm going to place an input pin to rotate it. So this input pin is also VDD. So we have VDD here. Here is the output of our power supply terminal. So connect this and then connect this one. So we place an output terminal. So same, and we're going to rotate this to 180 degrees and name it RB0. So that it is very clear that our output goes to this one. So we also can place ground or VXX. So terminal, then ground. Ground. Okay. Wait, that's the. So we just copy the following. So block copy. Okay, right click, and then we change the outputs. So this one, I think it is best if we do it descending. RB4, then this one is RB3, this one is RB2. And then this one is RB1. Okay, so I think our program is ready to be uploaded. So let us see and build the project here at MPLAB. So first debug the program for us to make sure if we made unnecessary mistakes. So let us wait, and then if it was built successfully, we can now build the program. So here you can see that our program is built successfully. Okay, so we need to build the program. So you can click either one of these. So clean and build project. so that we can get the hex file. So here, copy this and then paste it we can paste it here. So double click the microcontroller and then paste it here. And then click OK. After that, we need to load the program. So initially, our program, the output of the program is 0. So let us test the, so let us play again. Okay. When we have this one, okay, because of the delay command, there is a delay, of course, with the outputting of the value. And I also did not change the clock frequency. So make this 4 megahertz so that it will be a lot faster. So simulate again the program and then let us test all the outputs so that we are sure that it is working good working condition. So at first, no buttons are triggered, so the output is 0. And then when we trigger this one, it will output 1 because 0001 is 1. Next is we trigger this one, it will output 2. So if we need to output 3, we need to trigger both of these. So we are going to, if you see this button here, you are going to press this so that it will hold the push button. So 3. So for the number 4, we can trigger it here. 4. And then for the 5, we can trigger here. For 6, this one and this one. For 7, trigger it. Trigger RB0, RB1, and RB2. And then for 8, this one. 9, okay, 10 or A. So you have the A, and then B, and then C. Triggering C, we need 12, so 8 and 4. C, so 8 and 4. So C, and next is D. Sorry. So the next is D. This is D, and then E, we have here E, and then F if all buttons are clicked. So the program is good working because we simulated all of the inputs, all of the possible inputs, and then we also acquired the correct outputs from them. So here we outputted this following displays, and then we have already designed the 4-input hexadecimal decoder circuit. So we also follow the RB0 to RB3 as inputs, and then we use port C as outputs connected to a common cathode 7-segment display. So thank you for watching the video. Thank you for watching.